lasted, by the way, infinite amount of time, you will get a very funny distribution. There'll be more hot here than here. This means, by the way, that the entropy actually decreases. Entropy of this, compared to the entropy when all molecules are distributed within the whole container, is much smaller. This would violate second law of thermodynamics. Since 18-something hundred, when Maxwell came out with the solution physics and many and actual information theories and computer science were thinking how actually this cannot happen. And I think the thing that is relevant to us was Schiller in 1928, if I remember. He came up with a very interesting solution that actually show us that information is somehow related to energy, and information can produce energy. And the bottom line is here, but let me describe his idea. So what Schiller said, okay, let's have one molecule, only one. But I don't know whether it is on the left side or on the right side. Let's assume that a genie, a demon, an intelligence comes and tells you that the molecule is on the right. Then Schiller say, okay, replace this, it was the divisor, okay, some divider. Replace it with a piston. Keep it everything in the temperature, constant temperature. What this molecule does will be bumping this piston. And after infinite amount of time, this piston will move up here. So capacity V will be extended to capacity, to volume 2V. If you remember from high school, formula for free energy, it is something like K times N, number of molecules, times temperature T times log finite volume to the initial volume, and here is 1. So actually, by knowing where this molecule is, by the way, I can adjust to this piston through a weight here, and when this piston will move, it will actually inch my weight a little up. So actually, a real work will be done. And you can see that in this hypothetical situation, one bit of information, acquiring one bit of information equivalent to K times T, if you want log 2, 2 coming from the log 2, 2 times, because the volume at the end is twice as big as the volume at the beginning. Acquiring information actually requires energy, and that's how it is used to actually explain Maxwell's demon. But before it happened, Landauer came, and in '68, he told us what are the energetic limits for computation. And he, a very beautiful actually theory that together with Bennett they developed. He observed that there are certain operations that can be logically reversible and logically irreversible. And he was saying that those that are logically irreversible, which are also, he proved physically irreversible, then this operation in our computer will generate heat. And actually, in order not to violate second law of thermodynamics, one bit of information will actually produce about K2 log 2. That's what I showed you on previous slide, energy. Actually, the interesting thing was that he proved that storing one bit information, reading one bit information, and transmitting one bit information does not require energy. You can build reversible computations that will not require hypothetically any energy. The entropy will be disseminated only if I erase information. And Bennett came up with explanation to Maxwell's demon. He said, okay, demon has to observe molecules and has to have a tape, a storage, when we'll store information about velocity of different molecules. At the beginning of the state, it's a random state. So we'll be writing this information about speed of molecules. But from time to time, he has to actually, so you start with a random tape. This is the easy way to explain. from time to time, he has to write a new information. He is to change 1 to 0. In order to do it, he first has to erase 1 and then store 0. But when he's erasing, he is disseminating entropy. So a system that contains of the container plus, okay, I don't know if I find, okay, no, that's not the way to go. The system, container molecules plus demo together, if you compute entropy, you will find out that it actually increases. So we're okay. Everything is fine. We have about 5-10 minutes, I guess. So let me go through quickly through examples. I start believing, and I say something that I shouldn't, but I will, that biology, which is wonderful science, of course, but it's still in pre-Newtonian stage, when physics was before Newton actually developed his theory. That's not my saying, by the way. Somebody else made a statement. Because if you think about how many theories do we have in biology, probably Darwin is the only theory that we have. We have a lot of collection of facts. And of course, people are trying to put these facts into bigger theory. The problem is that life is extremely complicated. It's much more complicated than the real world that we observe. For many reasons, like quantum mechanics, quantum world is much complicated. But I think we agree that in a sense, what's happened in living cell, is some kind of a dance, interplay between energy, entropy, and information. Information is cells, living cells can die, but information doesn't. It is not physical paralysis. So there is, in living cells, there is something that I call information transfer. And perhaps the needed abstraction to build theory around biology could be actually trying to understand information transfer in living cells. Here's one example. I just learned it from my son. So you have a cell with the nucleus, and actually there are microtubule transports. So there are certain, for example, mitochondria that are either transmitted from the nucleus to the boundary of the cell or reverse. It turns out that this transfer, when it happens, it is not a smooth transfer. Actually, it is zigzag. And they are trying to understand why. Okay, maybe, so here is the conjunction, maybe the reason that we have sometimes this information transmitted slow because timing is everything when transmitting information leaving cell, and actually you have to deliver that information at a given time, within a given range of time, because otherwise it will probably destroy cell. Look, if this is very hot, and I'm trying to touch it, if this information about this hot is not delivered to my brain within a time, within a certain range, it will be a complete disaster. So actually, information living cell is definitely related to timing. So we have to understand this aspect, and we cannot understand it in a simpler sense. Other thing, we know very well that certain parts of DNA and other proteins, whatever, are better conserved than the others. Why? Because there is a Darwin selection and so on. But perhaps there is something else also. If you consider exon part and neutron part is non-coding for exon part when genes are, and genes are much better preserved. Maybe this intron part has a lot of bits, and actually what they do, they correct. So like error correcting code when we transfer information from one computer to another, maybe they actually are able to correct certain errors that occurs within the biological sequence. We don't know. Is it any way to actually study it? We are writing a small paper about this, but we try to understand mutual information for different parts of DNA, and it seems to be that there is some statistical dependency between exons and introns